Alright, this video is for Math 1050, section 8.5 in the book, Binomial Theorem, objectives. Just before I get into this too far, your graphing calculator, or any calculator that's a scientific calculator, is essential for these problems and being able to apply the binomial theorem, because factorial is a big part, but also combinations are huge in this case. And so we all know that factorial means to do descending multiplication, and you really don't want to do that by hand. So being able to have a calculator that will do these things for you is going to be key. It will save you a lot of time. So objectives, you want to be able to determine the binomial coefficient. Remember, binomial is a two-term expression. You want to be able to apply the binomial theorem, be able to use your calculator to find combinations, and with that I'd also put factorials, but we've already done factorials in section 8.1, and then finally we're going to find specific terms in binomial expansion. Alright, to understand binomial expansion and how there is a shortcut to it, is basically we use what's called Pascal's triangle, and I'm not talking about the character off of Tangled. I am actually talking about a mathematician in history. Anyways, Pascal's triangle is actually really easy to recreate, but it's kind of tedious if you have to go too far. So basically what we're looking at is, I'm going to put in a couple of numbers here. So this represents, well, I'll get into that, but you can see I'm just changing my value by 1. Okay, so what I've got here is that this first one in my triangle is going to be equal to 1. And then my second row is going to be 1, 1. And then my third row is going to be 1, 2, 1, and I get the 2 by adding these two numbers. My third row is 1, and I add these two numbers, 3, add these two numbers, 3, 1. My fourth row is 1, and you can see that we basically just keep adding to get the next numbers in the sequence for each row of Pascal's triangle. And then you can also see that we always have 1 at the beginning and we always have 1 at the end. So 1, this will be 5, 10, 10, 5, and 1. Okay, so that's basically how you create Pascal's triangle. So now, why is it useful? Basically, if I have a binomial like a plus b and I raise it to the second power, the numbers in row 2, or n equals 2, sorry, of the Pascal's triangle are going to be my coefficients for my expanded trinomial here. So there's 3 numbers in this row. So I'm going to have a squared, because it is a squared term, plus 2ab plus b squared. So Pascal's triangle gives me the coefficients for this binomial expansion. Okay, so just for another practice, let's do a plus b to the third power. So if we use it, we're going to have 4 terms. So we're going to have a cubed, because it is a third term polynomial, plus 3a squared b plus 3ab squared plus b cubed. So we got 1, 3, 3, 1. The numbers that we have in this row of the triangle. Okay, so now we're going to go to make some kind of connection. We're going to go dot, 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 dot here. And we're going to say Actually, let's not do the dot dot dot. Let's just look at 5 for right now, because I want to keep it in terms of numbers. So if I am doing a plus b to the 5th power, I've got my coefficients written out, but to be able to keep track of my exponents, I'm going to write them out. So my first term is a in my binomial, so I'm going to have a to the 5th, and then I'm going to have a to the 4th, and then I'm going to have a to the 3rd, a to the 2nd, a to the 1st, and then a to the 0, which is just 1. Okay, then with my b, since that's the second term in my binomial, I'm going to start with it on the right side of my equation. And so I've got b to the 5th, b to the 4th, b to the 3rd, b to the 2nd, b to the 1st, and then b to the 0, which is also 1. Okay, so these are going to be each of my terms, and now I just have to add my coefficients in. Okay, so we know we start out with 1, and then the next number in the row is 5, and then we have 10, we have 10 again, and we have 5, and then we have 1. And that's how you can use Pascal's triangle to write out your expanded form of the binomial. So if you notice, the big thing is for the first term, the exponent goes down by 1. So we got 5, 4, 3, 2, 1, 0. And then for the second term, it goes up by 1. So we have 0, 1, 2, 3, 4, 5. And so that's basically how this kind of a problem works. So let's say I want to do a plus b to the 7th power. So this is like one of the problems they ask for in the book. So if I'm going to do this, I've already got 5 done on Pascal's triangle, so I'm just going to write it out a little further. It'll make it easier. I'll have my coefficients 15, 6, 1, and then 1, 7, 21, 25, 25, 21, 7, and 1. Okay, so there's my coefficients. So now I can go, I'm going to put my a's down first. So I got a to the 7th, a to the 6th, a to the 5th, a to the 4th, a to the 3rd, a to the 2nd, and then just a to the 1st. So we got 7, 6, 5, 4, 3, 2, 1. And then I'm going to start with my b's on the right side. So b to the 7th, b to the 6th, b to the 5th, b to the 4th, b to the 3rd, b to the 2nd, b to the 1st, and then b to the 0. Okay, one other thing just to point out about expanding these binomials is that if you actually add the degree of each term, each of them are 7th degree term. 7, 6 plus 1 is 7, 5 plus 2 is 7, 4 plus 3 is 7, 3 plus 4 is 7, 2 plus 5 is 7, 1 plus 6 is 7, and then 7 again. Okay, so now all we're going to do is we're going to add our coefficients. So we just write the numbers that are in the row of Pascal's. So we got 1, 7, 21, 25, 21, 7, oh wait, I forgot a 25, 25, 21, 7, and 1, and then we add each term, so we can just put a plus. Alright, so before we get into this too much further, I wanted to give one more example where it's not just a plus b. So let's say, for example, we're talking about x minus 2. Actually, let's change this up a little bit, make it a little more complicated. Let's say we've got 2x minus 3. And we're going to raise this to, we haven't done 4, so let's do the 4th power. Okay, so 2x is my a value. So first I've got 2x to the fourth, and then I have 2x to the third. Notice that I'm putting it in parentheses so I can remind myself that I'm not just raising x to the exponent, but I'm also raising the 2 to the exponent. Then I have 2x squared and 2x to the first, and then I'm done with 2x. Okay, now working backwards here. This 3 is negative because it's minus. So we got negative 3 to the fourth. Then we have negative 3 cubed. We have negative 3 squared. And we have negative 3 to the first, and then negative 3 to the 0, which is just 1. Okay, once I have those written out, I'm going to write out my coefficients from row 4. So 1, 4, 6, 4, and 1. Put our addition in here. This problem looks very Christmassy, which is very appropriate for me. Okay, now we're just going to simplify with our exponents. So 2 to the fourth is 16, so this will be 16x to the fourth. 2 cubed is 8 times negative 3 times 4, so we have to figure out what that is, which is negative 96. So we got minus 96x cubed. Then we have 2 squared, so we got 6 times 4 for 2 squared, times negative 3 squared, which is 9. So we have, I want to say 216. So plus 216x squared. Okay, then we have 4 times 2 times negative 3 cubed, which is negative 27. And that is equal to negative 216 in this case. So we have negative 216 plus x to the first power. Then we have negative 3 to the fourth power, which is 81. And so that's what this would simplify to if we were to use or to do binomial expansion. And notice that this is a lot easier than to go and write this out as 2x minus 3 times 2x minus 3 times 2x minus 3 times 2x minus 3. And then multiply these, and then multiply these, and then multiply them by each other. This is actually a lot easier to be able to do it this way, and so that's why it's a useful shortcut. Okay, although Pascal's triangle is actually really easy to create and to keep going with, who actually really wants to go on it forever to say, let's say we were going to raise a binomial to the 100th power. So we actually have a shortcut for being able to find a binomial coefficient, so a coefficient in a specific location. So basically what we've got is that n is still our exponent, whatever the binomial is being raised to, and then r is the term that we're looking at. Okay, in Pascal's triangle, if we were looking at this really quick, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, 6, 4, 1, and so on. Basically, R is that we start this row of ones here is when R is equal to 0. This next diagonal is when R is equal to 1. This next diagonal is when R is equal to 2. And this next diagonal is R is equal to 3. This would be R is equal to 4. Okay, so basically when you think about it, we start out with term 0, then we go 1, 2, 3, 4, and that's how we figure out what term. So if I'm looking for the actual fifth term in the polynomial, I am looking for term 5 minus 1, because we actually always, the first term is equal to 0. So R is equal to the term minus 1. So basically, to find a binomial coefficient, we use this notation right here of n or r, like this. To represent the binomial coefficient, and that is actually equal to the formula of n factorial over r factorial times n minus r factorial. Okay, so that's a lot of factorial to it. So we also refer to this notation as n choose r, and this is actually an algorithm that exists on your calculator. You find it under your math probability option on your scientific calculator. And so basically what you do on, not scientific, graphing calculator, what you do on one of the older calculators is you first put in your n value, then you go to this option, and then you're going to put in your r value. And that's going to give you, if let's say I said I want to figure out 100, so raising it to the 100th power, and I want to know what the 64th term is, so I'm going to plug in 63 here. That means I'm going to do 100 choose 63. I would put that into my calculator, and I would get a ridiculously large term in scientific notation of 3.42 times 10 to the 27th power. And so that's binomial expansion right there. It's pretty useful, particularly if you can find this algorithm in your calculator to use to be able to find any binomial coefficient. Alright, so actual binomial theorem is basically talking about what we already did, but using the binomial coefficient formula or notation to do it. So if we think about it, let's go back to our a plus b to the n power. We don't know what n is, so but we know with Pascal's triangle it should be 1a to the n. But if we're going to use binomial, the binomial theorem, we would say that this is n0 times a to the n. And so that would be the first one. Any n value over 0 is going to be equal to 1, just so we all remember this. Okay, then our next term would be n choose 1 times a to the n minus 1 and b to the first power. Then our next one would be n choose 2, a to the n minus 2 and b to the second power. And so we can keep going until we get to, let's say, n choose n minus 1, whatever that ends up being. And this would be times a to the first power and b to the n minus 1 power. So notice that the exponent for b is always the bottom number in the parentheses here. And then finally plus n choose n, which would be a to the 0 power, just 1, and b to the n power. And so that's your binomial expansion theorem. We can also write this as a summation, applying it to sequences that we've already been doing, where we would say that r is equal to 0 to n of n choose r raised to the a n minus r and b to the r. And so that's how we would write it, as a summation. Alright, so that's pretty much the binomial theorem. Let's just practice one more type of problem here. So let's say we have 2t to the 4th minus 3b and we're going to raise this to the 6th power. Okay, and let's say I want to find the 4th term. Okay, so remember that r is equal to the term minus 1, so this will be 4 minus 1. And in this case, n is equal to 6 because that's our exponent. Okay, so this term is going to be 6 choose 3 of 2t to the 4th raised to the 6 minus 3 power times negative 3v to the 3rd power. Okay, remember, this goes here, and then the difference of these two numbers goes right here. Okay, so now we're just going to simplify this. 2t to the, t to the 4th to the 3rd power times negative 3v to the 3rd power. Let's simplify this down. So we've got 8t to the 12th times negative 27v cubed. And when we multiply that, we're going to have negative 216t to the 12th v cubed. All right, now we're going to use our combination. So 6 choose 3 in our calculator to figure out what that is equal to. And it's equal to 20. So we've got 20 times negative 216 t to the 12th v to the 3rd. So we multiply these two, and we get negative 4,320 t to the 12th v cubed, and that would be the 4th term of this expanded polynomial.